Okay, so what we're doing here is a brief review of probability. What are our learning intentions? We want to look at basic probability, we want to look at tree diagrams, probability tables, conditional probability, and independent events. Okay, let's start with, I'll just grab a pen here. Okay, a six-sided dice is rolled. What are we trying to do? What's our sample space? So things that we want to know about. Sample space, which we're calling E for the universal set. Here are the possible outcomes: 1, 2, 3, 4, 5, and 6. They're the possible outcomes. An event is a subset of the subset of the original. So if we say let A stand for we get an even number, then A contains the elements 2, 4, 6. Let's say B is our number is greater than 6, greater than 2, then B contains the elements 3, 4, 5, and 6. What sorts of things do we know about? We know about the union. The union means everything which is in both sets. So in this case, the union, A union B, I use that U shape for union. Everything which is in both sets is 2, 3, 4, 5, and 6. Notice each element only gets counted once. Even though the 4 and the 6 are in both, we only count them once. The other thing that we know about is an intersection. Intersection is what's common to both sets. And we use A intersection B, so this N shape for intersection. It's like the N shape. The intersection, what's common to both, is 4 and 6. It's in both 4 and 6. Right. Let's use this in probability. So here's a deck of cards. We have a deck of cards. One card is drawn at random. What is the probability? Probability that the card is an ace. Well, how do we work that out? We go with PR for an ace. We say there's 52 cards in a deck. There's 4 of those are aces, so it's 4 out of 52. That can cancel down. 1 out of 13. Let's go, what about the probability we get not a heart? So we're looking for the probability if I say H stands for hearts, I put this little dash, which means the complement of heart, not a heart. So that equals 1 minus the probability that I do get a heart, which is 1 minus 1 out of 4. Every fourth card is a heart. Gives me 3/4. What about if I said either an ace or a heart? What would that be? Either, when I say or, I'm thinking about the union. So that would be an ace union with a heart. I'm either happy to have an ace or a heart. Well, let's think about that. That's going to be the probability of an ace plus the probability of a heart, but there's also going to be the ace of hearts, so minus the probability of a intersection, minus the probability of the intersection. So that's every 1 out of 13 is a heart and an ace. Every 1 out of 4 is a heart, but there is 1 ace of hearts that we're not counting. So we end up with 4/13. So need to think about this one, this particular rule. Probability A union H is the probability of A plus the probability of B minus the probability of A intersection H. That's important. Okay, the tree diagram is our next one. A coin is tossed 3 times. Well, here's our first toss. We can get a head or a tail. Our second toss, we can get a head or a tail. A head or a tail. Our third toss can get a head or a tail. A head or a tail. A head or a tail. Head or tail. And now you say, well, what's the sample space? Well, I've got head, 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 tail. I'm following along the arrows. Head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 head, tail, tail, tail. And you say, well, what's the probability associated with each of these? If this is a fair coin, this is a half each, so 0.5 and 0.5. So if it's equal, we can put the probabilities on each, and then we say, well, I want the probability of getting head, head, head. That's going to equal a half times a half times a half. 2 2s are 4, 2 4s are 8, so that's an eighth. You might say, what's the probability of getting two heads? Exactly 2 heads? Well, here's exactly 2 heads. Again, that's a half times a half times a half, so they're all going to be 1/8. Here's exactly 2 heads. Here's exactly 2 heads. I don't care which order. This is 1/8. This is 1/8. So the probability 2 heads is 1/8 plus 1/8 plus 1/8. Which is 3/8. Okay, now we want to talk about a Karnaugh map or a probability table. Here we go. Simone visits the dentist every 6 months. The probability she needs her teeth cleaned is 0.35. The probability she needs a filling is 0.1. The probability of both is 0.05. So what we're going to do is draw our probability table. We're going to say clean, not clean, filling, not filling. These are our possibilities, and each of these represents a particular value. So what are we going to say here? This is the situation, this is the intersection, a clean and a filling. This one is a clean but no filling, the intersection. This one is no clean but a filling, and this one is a no clean and no filling. Now you say, let's draw that same table again, only this time we'll put the actual values in. So we've got clean, not clean, filling, not filling. And we're going to say, well, they've told us that the probability she needs her teeth cleaned is 0.35. So this column here has to add up to equal 0.35. The probability she needs a filling is 0.1. So this column has to add up to equal 0.1. They've told us the probability she needs both, the intersection between a clean and a filling, is 0.05. We can work out the remaining values by saying, well, this column has to add to equal 0.35. We've already got 0.05, so this has to be 0.3. This row has to add to equal 0.1. We've already got 0.05, so there's going to be 0.05 there. Then you say, hang on a minute, the possibility of anything happening, something happening, is 1. So this row has to add to 1. We've got 0.1, so here's 0.9. This row also has to add to 1. We've got 0.35, so this is 0.65. And then you can say, well, the missing value, this is 0.05. It has to add to 0.65. This is 0.6. Check by going this way. 0.3 plus 0.6 is 0.9. So from there, we can say, well, what's the probability that she gets no clean and no filling? Well, that's going to be 0.6. We just read it straight off. The table. Okay, conditional probability is our next step. What do we mean by conditional probability? We're talking about the probability of A given B. So this means for B. So we say what we're talking about is the probability of A occurring given that. So given that B has already occurred. I think there's only one R there. So, and we write that as the probability A given B. So this line means given. How do we work that out? It's the probability of A intersection B divided by the probability of the thing that's already happened. The intersection of the two things divided by the intersection by the probability that that thing's already happened. Let's look at an example here. And I'm going to fill in a bit of a table here. Here's some students rate the canteen. And it's quite a big table here. We've got 10s, 11s and 12s. We're going with poor, good, excellent, and we're going to have totals at either end. So let's fill in our values. Fill in our values here. So there are 30 kids in year 10 that thought the canteen was poor, 80 thought it was good, and 60 thought it was excellent. And that gave a total 170 kids in year 10. 20, 65, 65 gives me a total of 150 kids in year 11. And 10, 35, 35 gives me a total of 80 kids in year 12. That gives me 60 kids rated it as poor. I'm counting along the rows now. 180 rated it as good, 160 rated it as excellent, and that gives me a total. My totals have to match rows and column of 400 kids. So let's go. What's the probability? So the question here, what is probability that a student is in year 12? Well, we look at that. Probability of being in year 12. There's 80 kids in year 12 and there's 400 kids in total. So 80 over 400 gives me 1 out of 5. What's the probability? So part B, I'm going to go over the page and then come back for this one. Oh no. Yeah, I will. So now I want part B. I want the probability the student is in year 12. In year 12 and rates canteen as excellent. Well, let's have a look at that. We'll go back to our table. We're looking for in year 12 and rates a canteen. Oh no, wrong way. In year 12 and rates a canteen as excellent. Well, E, what's that? We're looking for in year 12 and rates a canteen as excellent, 35. So there's 35 kids who are in year 12 and rate the canteen as excellent. So that gives me, that can cancel down 7 out of 80. Now, is in year 12, given that they have rated the in year 12, given that they have rated the canteen rate as excellent. So you have to think about this one for a minute. We're in year 12, so what we're looking for is the probability that you're in year 12 given that you've rated the canteen as excellent. So we need the probability that you're in year 12 and that you've rated the canteen as excellent. So divided by the probability that you're in year 12. So how does that work? Well, the probability that you're in year 12 and excellent, and we've just worked that out at 7 over 80. What's the probability that you're in year 12? Oh no, sorry, I've written that incorrectly. Scrub that out. We're looking for the probability that you've rated it as excellent. So let's go back. What's the probability that you've rated it as excellent? Well, let's see. Excellent, there were 160 kids out of 400. So, probability of excellent is here. Rate of an excellent rating is 160 out of 400. That might be able to cancel down. What does that cancel down to? 16 over 40 is 8 over 20 is 4 over 10 is 2/5. So this big one, that's just a little aside there, becomes 7 over 80, which was our answer up here, divided by 2/5. Now you remember when we divide by something, we invert and multiply. 7 over 80, that should be, not 18. 7 over 80 times 5 over 2. What does that give me? 7 over 32. Okay. The next one I'm going to try, and this we're going to go with D. Rated canteen as excellent, given that they are in year 12. So let's see how we would write that again. So we're looking for probability, rated the canteen as excellent given that you're in year 12, means the probability of excellence intersection with year 12, this time divided by the probability that you're in year 12. Now we've done that one already. Again, top line becomes 7 over 80, bottom line becomes 1 over 5. They're two answers from previous sections. 7 over 80 times 5 over 1 gives me 35 over 80, which gives me 7 over 16. Okay. Last thing I want to talk about is independent events. So we're looking for the probability. The thing about independent events are independent, that means they have no influence on each other, if the probability of A intersection B is the probability of A times the probability of B. So flipping two coins is independent, the coin can't remember, so they're independent. So the flipping, getting two heads is the probability of getting one head times the probability of getting another head. That's what we mean by independent. So here's our example. Here's the probability, Monica does her homework is 0.7. Good girl, Monica. Here's the probability that Tom does his homework is 0.4. I want to know what is the probability they both do their homework. So probability that Monica and Tom, so and is intersection, both do their homework is 0.7 times 0.4. Because these are independent events, I can just multiply them together. What's the probability that Monica does do her homework and Tom doesn't do his homework? Well, that's 0.7 times 0.6, 0.42. So that's a bit more common, bit more likely. Okay. During this presentation, I've talked about basic probability, tree diagrams, probability tables, conditional probability, and independent events. So you should be able to have a go at the exercise now.